Okay, this is an example of proof by induction with inequalities. And the idea of proof by induction is that we take a base case and prove it's true for the base case. In this case, the base case will be n equals 4 because we're seeking to prove that it's true for all n greater than or equal to 4. And then if we can prove that it's true for n equals 4, and then just prove in general that if it's true for k, it's true for k plus 1, effectively what we've done is then kind of prove that it's true for 4, 5, 6, 7, all integers beyond 4. So that's the idea. So we need to do the base case first. So let's just consider the base case. Base case when n equals 4. Well, 4 factorial, which is the left-hand side, let's call that the left-hand side, 4 factorial equals 24. The right-hand side, 2 to the power of 4 is equal to 16. And because obviously 24 is greater than 16, we can say the left-hand side is greater than the right-hand side. So therefore, the statement is true. True when n equals 4. Okay, now we're going to say, we're going to go to the point where we assume true for n equals k. So we're assuming it's true for n equals k, say. They're just using we need a different symbol to n because because we want to prove the iterative bit. So we're going to then, so that means we're assuming that k factorial is greater than 2 to the k. Now we can consider the kind of, this is sometimes called the inductive step. It's the kind of crux of what we're doing. We'll consider the case when n equals to k plus 1. Remember, we're allowed to assume, and this is the whole point, we're allowed to assume this is true in this step, and we will be. That's how induction works. So we can then say that k plus 1 factorial, that's the left-hand side, equals k plus 1 factorial. Now, that's k plus 1 factorial is equal to k plus 1 times k factorial. Right, now, we are allowed to, this is where the assumption comes in. So we are now allowed to assume that this is true. So we can say that that is greater than k plus 1 to the 2k. That's the assumption. That's where the assumption comes in here. That's where the assumption comes in. So we can therefore say that we can therefore say that that's k that's certainly greater than 2 times 2 to the k, since k is greater than or equal to 4, because we certainly want, we're not seeking to prove it for anything less than 4. So for anything greater than 4 is definitely greater than 2. So that actually is the same as 2 to the k plus 1. So now we've shown, which is the right-hand side, we've shown that the left-hand side is greater than the right-hand side. In other words, if it's true, so that's, we can close off with our conclusion because we've basically done it. But we do need to conclude. If we've shown that it's true for one case 4, Okay, the base case. And we've shown, given the assumption it's in general true for the next one after any given k. So if k were 4, we've proved that it's true for 5. If k were 5, we've proved it's true for 6, and so on. Iteratively, we've proved it for all integers, positive integers greater than 4. Because we've basically got, I should write it again maybe here, we can say that k plus 1 factorial is definitely greater than 2 to the k if true, 2 to the k plus 1, if true for n equals k plus 1. Okay, so since the base case is also true, it follows the statement is true for all n greater than or equal to 4. And we are assuming, of course, that n is a positive integer or positive natural number. But at this level, it's probably not necessary to say that for this proof, but strictly speaking, we should do. So that's it. We've basically started off showing the base case there. Then we had the assumption there. We used the assumption here in our work for what's called the inductive step. That's all kind of come into here. And then this bit here at the end is kind of a conclusion, bringing the whole thing together, concluding the whole thing. I might use a nice little implied sign there just to kind of close it off. But that's how induction works for an inequalities question. Okay, that's it.